test for a single population mean. So we'll do this through an example. We use an injection molding process for pen barrels. And let's suppose that the nominal outside diameter of the pen barrels is supposed to be 0.380 inches. And lately, the supervisor in the packaging part of the process is complaining that the caps are falling off and they're jamming up his equipment. So we need to determine if the outside diameter of these barrels, on average, has become too small. So in other words, we need to identify whether the problem that's occurring is due to the fact that our pen barrels are actually just too small. This is a test for a single mean because there is a single population of pen barrels and we have one particular target value we are interested in, namely that their outside diameter is 0.380. The only way to know for sure if a process is actually shifted is to measure every single output that's coming out of that process. Of course, this is not a practical way of doing things, so what do? We, of course, take a sample. Let's suppose that the sample gives a mean of 0.379. Remember that the target is 0.380. We might feel comfortable with 0.379 saying, yeah, it seems close enough to 0.380 that everything is probably okay with the process. But what if that is now a little lower, 0.377? We're going lower here because our focus here is that the pen barrel diameters are too small. Well, maybe. What about 0.370? Well, that's starting to get a little bit far. In either way, looking at any of these values, it will be impacted by the amount of variation that's in the process. So if there's a very tiny amount of variation in the process, even shifting to 0.377 might be alarming enough to us that we would consider that to be a problem. On the other hand, if there's lots of variation in this process, it makes diameter of pen barrels all over the place, then even something as far away as 0.37 might not seem that unusual under the variation for our particular process. What if it gets to, say, 0.342? I think eventually we can get to a place that everybody would say, there is a problem, this is clearly far enough away, something major has happened, we probably don't even necessarily need statistics to make that decision. So let's focus on what we call one-sided tests. And our example with the pen barrels is a one-sided test because we only need to determine if the outside diameters of the pen barrels, on average, are becoming too small. So we are only focused, say, on the lower part of the distribution. So if we look at a picture here, the red curve is representing actually being on target, the process representing on target at a mean of 0.38, and what we are considering is has that process shifted down, and in particular, it's been drawn as shifting down to 0.37. So this is what we're trying to detect, and we do not care if that curve actually shifts to the right, we're only interested in whether it's shifted down, and the diameter of the pen barrels are too small, and that is why the pen caps are falling off. So for continuous data from a well-behaved distribution with an unknown value of sigma, then we would estimate sigma from sample data using the S, the standard deviation from the sample, and we use for these type of situations what's called a t-test, and in particular a one-sample t-test. So let's collect some data. So went out to the process, they took a random sample of 15 pen barrels and yielded the values there. And the question is it clear that the outside diameter is lower than 0.38 from just looking at that data? You'll notice that there are 4 or 5 values that are on target. There are a few values above, and there are more values below than there are above. but it's not clear just looking at the data whether that's enough evidence to say that it has shifted. Okay. Also notice that there is a sort of discrete nature to this data, whether it's due to rounding of the values or that the precision in the gauge can only measure to 3 decimal places, is sort of creating a four distinct levels here, and that is it. So let's consider a hypothesis test. Our first step would be to state the hypotheses. In our example, the null hypothesis is that we are on target, or we are equal to the 0.38, and in particular, we are only concerned with whether it is shifted down and our outside diameters are too small. We would need to state the test statistic in step 2. We will use a t to represent this because we're going to use a t-distribution here. And the numerator represents y bar minus the target value of 0.38, which we'll call mu0. And the bottom represents s, the standard deviation, divided by the square root of n. Now it's important to break those into numerator and denominator and think about it just in terms of English or words to try to see what's going on here. So let's look at the top. One way to talk about the top is it's just a distance. Y bar is measuring where you're at from this particular sample, and mu0 is measuring where you're supposed to be, the target value. So this difference is just a distance. And one can imagine that the bigger that distance is, the more likely that something is going on, that we've shifted, something has happened. However, there are many ways to get the same y bar value, different numbers in a sample that would yield the same mean. And so we need to consider how much variation is in the data before we just look at distance. So in statistics, we're always looking at distance relative to variation. If this value is large, t is large, that is saying that the distance we're observing is unusually large relative to the amount of variation in the process, and most likely means something has happened. Step 3, we would state the critical region, and this depends on the alternative hypothesis. In our case, we're looking at a less than hypothesis, so we are only looking at the lower part of the curve, and we're trying to decide, well, how large is large? That distance over variation, how big can that be? And so what we define is an area of alpha in the corner. We call that alpha is the probability of a type 1 error. And we define a t-value there called t alpha that says anything bigger than that, okay, will be considered unusual. So we will reject the null hypothesis and claim something has happened, that the pen barrels are too small, if our t that we observe is less than this t alpha value off of some sort of t-table, the n minus 1 representing the degrees of freedom. We could also look at a greater than hypothesis and just flip the curve to the other side, and we would still be looking at the same type of value, t being bigger than some t alpha value. Common values for alpha are 10%, 5%, and 1%, with 5% being the most popular choice. So if we use 5% in our particular case, our pen barrel case, then we will reject if t is less than minus t of 14 degrees of freedom and a 0.05 value. So if we look that up on a t-table or use a computer software package to find that value, we'll find that that value is 1.761. So if our t, our distance over variation, exceeds negative 1.61, then we would claim that something has happened and that the pen barrels have probably been made too small and something needs to be. Well, step 4, we have to conduct the experiment and to calculate the test statistics. So we take our data that we had from our sample, and we find the mean, and we find the standard deviation. Then we run it through that t calculation. So we take our mean from our sample and subtract the target and divide by the standard deviation over the square root of the sample size. and that turns out to be minus 2.152. So, comparing that to our value from step 3 in the critical region, notice that our t-value, minus 2.152, is less than minus 1.761. It is further in the extreme. So we have sufficient evidence to reject the null hypothesis. Or in English, we therefore have enough evidence to suggest that the outside diameters, on average, are less than 0.38. So the problem could be coming from us. Now, most software programs, on the other hand, will use a p-value instead of a critical region. The p-value has kind of a long definition. It's the probability, assuming H0 is correct, of observing a test statistic as extreme or more extreme in what direction, the direction of the alternative hypothesis, than what we actually observed in the sample. So it's sort of giving you a probability of how unusual the value you saw was. We call this a lot of times the observed significance level. So if we look at it mathematically, it's the probability from a t-table that we're less than the test statistic for our particular example, because the direction of HA is less than. So the probability that t is less than our minus 2.152 turns out to be 0.0246. So we're basically giving us the probability that we would observe something as unusual or more unusual than 2.152 would only occur about 2% of the time if the process was actually on target at 0.38. That's the assuming H0 correct part. We reject the null hypothesis if the p-value is actually less than alpha. A small p-value means that we observed a very unusual case, assuming the null was true, which may indicate that the null was probably not true. So picture, it's easier to think about. So here's a figure for our particular example, and one can see that the negative 2.152 there, that the probability of being below it is kind of got some lines on it there on the graph, and is showing that it's 0.0246. Notice where the critical region was. That's the 1.761 or negative 1.761 that we were using. Notice that if the test statistic is below or in the critical region, minus 2.152, it automatically makes the p-value smaller than the area that's below the critical value, which is alpha. So notice why this is how it works. If the test statistic is in the critical region, that automatically forces the p-value to be smaller than the alpha value. So that's where that decision is coming from. These two things cannot reach different conclusions. They are linked directly together. So since our 0.0246 is less than 0.05, we reach the same conclusion as we had from the critical region. Therefore, there is some evidence to suggest that the outside diameter is less than 0.380. A reasonable question when we reject the null hypothesis is, what are plausible values for the true mean diameter? Where are they actually at? We can construct a 95% one-sided confidence interval here for the true value of mu. This interval would run from minus infinity, basically, to an upper bound. Notice we do not need necessarily a lower bound in this case, because anything low is bad. So we're just sort of want to get that upper bound and see, is that value good enough or not? So we're just doing a one-sided interval, and we can just write it as an interval if we want by putting infinity in there. So if we crank through the math and run through that interval, then we get this interval here, 0.3799 basically. So what we're saying is we're 95% confident that the true mean outside diameter is something less than 0.3799. Does the interval contain our target value? some sense, we could have just drawn this interval, this confidence interval, and just checked if our target was in there. Since it is not one of the plausible solutions. What did we assume to do this analysis? Well, that our outside diameters follow a well-behaved distribution, symmetric, single-peaked. Are we comfortable with that assumption? Well, we could draw a stem and leaf diagram or a normal probability plot, something like this to verify. If we had a lot of data, one could use a histogram. Okay. Now, one of the problems we have here, as we mentioned earlier, is that kind of discrete nature, either due to rounding or the gauge, which forces all our values to only take on 4 particular values. So it makes the normal plot look a little weird with these straight lines going across. But if we think about trying to look at a line going through there, it's reasonable to assume that this distribution is roughly symmetric and possibly single-peaked. Now, on the other hand, we might look at a two-tailed test or a two-sided test. So, for example, our pen barrels, in a general sense, would be a two-tailed or two-sided test. In general, monitoring the outside diameter of pen barrels, being too small obviously causes the caps to fall off, as we saw. But if it's too large, the caps won't fit right, or they're too snug, you can't get the cap off. So in a general monitoring procedure or a general problem, we would consider both sides important. But in our particular example, we had a very real situation where they were only interested in the low side because of what was happening in the shipping department. So instead of carrying on with that, we'll just shift gears and talk about making wine. And one of the things that they look at is how good the grapes are, and relate the alcohol content to the sugar content in the grapes. And a particular Napa Valley winery pays a premium to its grape growers, wine grape growers, if they can deliver a shipment that has a true mean alcohol content of 26%. So we have a target of 26%. Too high or too low is not good. So the winery tests grapes from 5 different locations within a shipment. So you got a big barrel, say, and we're taking different samples to get a good representative of what's in the shipment. And what's an appropriate method for determining whether a wine? Well, we can use a hypothesis test. And the only difference from what we did earlier is that our alternative hypothesis is that it's a not equal to, meaning that if it's too large or too small, we're not going to pay a premium. The test statistic is unaffected by the alternative hypothesis, so the test statistic will stay exactly the same. On the other hand, the critical region is affected by the alternative hypothesis, and what we're going to do is look at both sides of the curve now. Now, to keep everything at a type 1 error probability of alpha, what we'll do is we'll just split it and look at both sides at alpha over 2. This keeps the type 1 error at the same level. So we will reject now if we just absolute value our test statistic because we don't know whether it's going to be bigger or less than the target. So we'll just make it positive, and we'll just compare it to the positive side. This just makes it easier. Notice the difference is that value off the table is using alpha over 2 now and not alpha. In our case, we'll go ahead and use 0.05 again, and we will reject the null hypothesis if we run through that t and look it up on a table or in a computer. We will get 2.77. So that is defining again that distance to variation ratio now has to be bigger than 2.77. Conduct an experiment and calculate the test statistics, step 4. Okay, well, we're not given the actual data in this example, but we have the mean and we have the standard deviation and the fact that they took a sample of 5, and that's all that's necessary to run through the t formula. So when we do that, we see that our ratio is negative 2.58. We could calculate the p-value from that. The difference in the p-value now is because we're only going to look at the positive side of 2.58 and find its probability, if we're going to compare it to alpha, we need to multiply that by 2 because we had split the alpha probability in 2. Okay, so to keep everything equal, we just multiply that back by 2, and we end up with 0.061 in this case. We could also construct a confidence interval. In this case, it would be an actual interval because we do care about both low and high. So we get an actual interval here. The difference, again, is that the t-value is using alpha over 2 here. If we run through that, we are 95% confident that the true mean for this shipment of grapes, the sugar content, would be between 22.9, say it's around, and 26.1. So we reach our conclusions and state them in English. Since the t-value, the 2.58 in absolute value, is less than 2.77, it's not bigger than that cutoff value, or our p-value is bigger, 0.061 is bigger than the 0.05, the alpha value, or our target of 26 is in our interval, confidence interval, any one of these ways of looking at it would all lead us to fail to reject the null hypothesis. Or in English, there's not enough evidence to suggest the sugar content is not 26%. So in other words, it does appear that this shipment achieves the 26%. Therefore, we should pay the grower the premium. Typically, we would want to check our assumptions and verify that everything is okay, but with n equal 5, such a small sample size, there's not a lot you can do. So we're just going to have to trust that the data come from a well-behaved or nearly normal distribution. Again, well-behaved is mainly meaning single-peaked and reasonably symmetric. So these two examples illustrate what we can do with a one-sample t-test, either with a one-sided hypothesis, a less than or a greater than, or a two-sided, which is the more common case where we care about things being too big or too small.